Kia ora Year 13. This is the second probability distributions video, and this one is looking at the idea of a fair game and the expected gain or loss. So in the ESA workbook, this material is on pages 191 to about 193. So watch this video, do the examples in here, and then go and do the work in that workbook. Okay, so big idea in probability is that if a game is fair, then the expected gain is 0. Sorry, not R0, is 0. Right, and in this video we are going to look at some really simple situations, but this was a really important idea early in probability, and lots of our quite sophisticated probability distributions come from situations where people tried to work out the probability of winning in games, and we'll look at some of those in much more detail in the next couple of weeks. So what we're going to be working with here is a discrete probability distribution where again we've got the probability down here and the different outcomes of playing the game. There are two ways to do these. You can think about up here as having the amounts you win. So you might win $1, $2, $3 or $4, and you might also pay an entry fee. We'll make the entry fee, I don't know, 10 cents. And you can have your probabilities down here. Remember, they've always got to add up to 1, so you've got to check that. So in this case, if we wanted to work out the expected gain from playing, we would do it by first of all working out the expected winnings, right, and then subtracting off the entry fee. Okay, so we would go like this, but that doesn't take account of the fact that the person playing this game always pays 10 cents to enter. So we take that off at the end. The other way to do it is just to work that in to the different x values, so that instead of showing the 10 cents separately, we adjust it in here. Okay, so this would be 190, this would be 290, and this would be 390. So you can do that either way. You can see that in the example I've done here, it's going to be far easier to do it at the end and work with these lovely round numbers here, right? Instead of 90 cents, $1.90 and $2.90. But it doesn't matter. So if you're trying to make a game fair, there are three things that you can do. You can muck around with the entry cost, the cost to play the game, right, the 10 cents. You can change the probabilities of winning if you can do that. That will depend on the situation. And you can change the amounts paid for winning. So we're going to explore a couple of those later on. Okay, so here's the silly example I came up with. So to increase the amount of money two kids get to spend at the shop every week, they have come up with a game for their mother to play. And they charge her $1 to enter. This was in no way influenced by real life. They set the timer on the oven, and they make their mother shut her eyes and yell stop. And when she yells stop, they hit stop on the timer. If the time on the oven ends in a prime number, she wins $5. If the time ends in a non-prime even number, she wins nothing, and otherwise she has to pay her kids another $2. You might suspect that the mother is a maths teacher. Anyway, work out her expected gain. So when you get a problem like this, you need to break down what are the different outcomes and what are the probabilities of them winning. So try and do this one now. I'll insert a slide here and put the solution in. So pause the video and work through that example. Okay, so what does the situation look like? Well, I'm going to do this working the expected gain into the payoffs here. Right, so we're going to have three situations. I hope you all remembered what prime numbers were. If the timer stops and the last digit is a prime, she gets $5. But she pays $1 to enter, so her net gain is $4. Okay, it's totally fine if you did this the other way. If she gets a non-prime even number, she doesn't get anything, and she's paid her entry fee. So that's 0 minus 1, So that's negative $1. Otherwise, she has to pay the kids $2, and she's already paid them $1. So that's negative 3. Now the next thing we've got to do is to work out which category is which. So this is prime, and this is non-prime even, and this is otherwise. Right, so what are our prime numbers between 0 and 9? Well, we've got 2, 3, 5, and 7. Our non-prime even numbers will be 0, 4, 6, and 8. And otherwise, well, what's left? 1, and basically odd numbers that are not primes, 2. So nice, easy probabilities, 0.4, 0.4, and 0.2. Okay, we'll get rid of those. There they go. So now we just work out what her expected winnings are, and we do that in the usual way. So E of x is equal to 0.4 times 4 minus minus 0.4 times 1 minus 0.2 times $3. Right, so E of x is equal to 60 cents. So this is saying that after accounting for everything, including the entry fee, the mother is winning. On average, she's winning a whole 60 cents. So that leads us to the next part of the example. Okay, the kids are unhappy, and you have been hired to give them some advice about what they should charge the kid's mother so that the game is fair. So you've been told here what your parameters are for mucking around with. You are expected to be changing the entrance fee. So we'll set that up like this. The probabilities aren't changing, so there's still 0.4, 0.4, and 0.2. Right, and so the payoff is now going to be 5 minus k, negative k, and the $2 she's got to pay them less k. Right, so k is the fee. Now you might notice here that it really is quite inefficient to solve this problem like this. So when you're mucking around with changing the entrance fee, it's going to be much better to separate that off at the end. In other words, we are going to work with the payoff being just the winnings, and then we'll adjust off the k at the end. So the expected gain is going to be 0.4 times the $5 plus 0.4 times the nothing plus or minus 0.2 times the 2, and then minus the k. If the game's going to be fair, that all has to work out to be 0. Okay, so I need a new slide. We are solving 0 equals 2 plus the 0 in the middle, so very easy to work out, minus 0.4 minus the k. Okay, so this is my entry fee, and that gives me k is equal to 1.6. So the entry cost should be $1.60. Okay, on to the next variation on this. Right, so now their mother suggests that they should leave the entry fee at $1, but change what they give her for winning when the oven timer stops on a prime number. So what amount should they make that be if her average loss is to be $1? Okay, so what we're trying to solve here is probabilities aren't changing again, 0.4, 0.4, 0.2. And then up here we're going to have the amount she wins for a prime. We'll make that k this time. She's going to get 0 for a non-prime and negative 2. And then the fee is $1. So her expected gain is going to be 0.4k plus 0 minus 0.4 minus $1 right? And we want that average loss to equal -1, okay? Because she's being nice and she's saying on average she's happy to lose $1 every time they play this silly game. Right, so just working that through, what do we get? Well, we get 0.4k equals -1 plus 1.4. 0.4k is equal to 0.4. So this is giving me k equals 1. So what that's saying is that if she gets a prime number, they should just pay her $1. In other words, in the situation where she gets a prime, she's going to pay $1 to join the game, and then they're going to give her back her $1. So she should win $1 for getting a prime number. Right, there's lots of good examples of those in the workbook, so go ahead and do some of those now. Thanks for watching.